Hey, welcome back to Fat Mama Physics. In this video, I am actually going to do a little bit of note-taking for us, and that is to kind of highlight some of the work that previous people have done. Along the way, there are a few observations and maybe a few equations that may pop up on your IB exam, so I wanted to give you some background information on how that came to be. It's one of those things that's not in your data booklet, and it pops in a question here and there, and it's just bothering me. So I kind of want to give you some heads up on that one. And also, it ties very nicely into our next topic, which is de Broglie's wavelength. De Broglie! Yes, that's how you pronounce that. Okay, let's get started. Planck and his research. So essentially, we have done Einstein's photoelectric effect. We've looked at Planck's constant and that Planck's relationship between the energy of a photon and its frequency. So let's give us a little bit of backstory. I won't make it too long, just to kind of give you an idea. So where did Planck come up with this constant and this E is equal to HF? So where did that come from? It actually came from his research on a black body radiation. So if you recall, black body radiation, here I have a y-axis plotting the intensity, and then along the x-axis here I'm plotting the wavelength. So for black body radiation, depending on the temperature, you get a different shape of your... That's my attempt at drawing it. You get a different distribution of intensities and the wavelengths and the respective intensities. And of course, as the temperature increases, you see the peak wavelength shift towards smaller wavelengths, as described by Wien's displacement law. Now, Planck looked at this data, and he, using classical physics, classical theory, was unable to explain the fact that basically as you approached, as you kept heating up your substance, you get essentially an explosion of this graph. So using classical theory, there's no way for him to be able to model this mathematically, which then he later came along and described how to get this to mathematically. He proposed that at higher temperatures, the oscillations of these electrons basically increased to the point where it will be able to release radiation of higher energy or that of lower wavelength. And he used a mathematical relationship to describe that. Essentially is based off of this, in which the energy released by this photon comes in these integers of h and the frequency of the particles. So more detail on that. But essentially the math involved that he used to describe was rejected by a lot of different scientists back in that time. Basically what he did is he kind of used a mathematical model to fit the data with very little theoretical backing to it that related to what people were accustomed to back in the day, which is the classical theory. So that's where this came from. So that's the first, this is kind of if you kind of want to say, it's one of those first experiments that kind of led physics down to the quantum world. So next comes Einstein and his work on the photoelectric effect. So he, as of course you know already, Einstein found that for an electron to be ejected off a metal surface is independent of the intensity of a light wave, but instead it had to do with the frequency of the light he used. So that he used Planck's relationship there to describe how light comes in these little packets called photons, carrying quantized amounts of energy that depended on the frequency of the light itself. And he eventually was able to confirm that through his work and looking at the work function of a metal. So essentially, he had data where he was able to measure the kinetic energy of the electrons that were fired off and in relation to the frequency of light he used. So this is the relationship he found, and very nicely, and of course it refers back to the previous videos on application of this, but essentially he was able to find that this relationship had to do with, of course, the work function of the metal, and then any additional energy was spent for speeding up this particle for its kinetic energy, essentially. So this is the amount, this is the light that photons that he used, work energy, the work function, so the minimum amount of energy to eject an electron, and the remaining kinetic energy. Now, very nicely, he was able to demonstrate that the slope of this graph is Planck's constant. So doubly confirming or supporting this relationship here. Okay, so that's where, so Einstein based off his work on that, and this E equals to HF has received additional research backing support. Of course, there are other ones, including the line spectra and many other research has is able to confirm or to show support for this relationship. So Einstein looked back at his special relativity work, and he used a bit of that and as well as this current finding, and he found this relationship. What this relationship is saying is that the energy of a particle depends on its rest mass and as well as its momentum. So if you think about this guy over here, this is like its kinetic energy. This one over here is like its rest mass. So that the total energy of this particle depends on its rest mass. So essentially, being able to relate the mass to energy and as well as its momentum, how fast it is traveling. So this is the one that tends to appear now and then in your data book, or not in your data booklet, in questions and things that you have to apply. So where does this come from, and why does it look this way? Especially with kinetic energy, it doesn't look exactly like 1/2 mv squared, and it doesn't even have the 1/2 symbol in there. So what does this mean? First of all, we have to appreciate Einstein's work on special relativity, which is when a particle's speed goes to the speed of light, we notice that it becomes harder to accelerate it. So from a relativistic point of view, to model that, it seems as if the mass of the particle is increasing. Well, essentially, if it becomes harder to accelerate, or if it seems like its mass increasing, whatever that is, we know that the force needed to move this particle or to get it to accelerate at higher speeds becomes harder and harder. So if we do the work, if we try to find the amount of work done to accelerate this particle, and if you know your calculus, if you don't, that is okay. Either way, the idea here is that because it is harder to move this particle, the amount of work done to get it to accelerate or to get it to speed up becomes harder and harder, which then breaks through, or it breaks away from our classical understanding of kinetic energy, which, according to the work energy theorem, the amount of work done you put in an object to speed it up is equivalent to its kinetic energy. But the work done in this case is the force that we have to use here is increasing. It's not constant. So when we take the integral, we get a different relationship. So here we have the classical model, which we know that Ek is equal to 1/2 mv squared. This is the kinetic energy as the particle is increasing. But to model this idea, which the faster the particle is, the harder it is to accelerate it, then this kind of looks like this on this diagram. For relativistic speeds, this deviates from our classical model. So this term over here, even though you might have, you're going to feel a little uncomfortable with that one, that's just because the particle is moving really fast. So this is what we use to calculate its kinetic energy. So at higher speeds, notice that the kinetic energy is modeled by PC, in fact. So that's E squared, that's PC, and all of it squared. So kinetic energy, we can use momentum times the speed of light when the particle is moving at higher speeds. What he noticed, if we take a look at this model here, this equation, we can see how if a particle is massless, then this equation reduces to E equals to PC, okay? So this MC squared, this goes away, for example, say a photon. So then the energy of a photon is going to be dependent on its momentum as well as the speed of light. Now, if we tie in the Plancks and Einstein relationship theory, E equals to HF, then we get something that looks like this. We also know that the frequency of the photon is the speed of light over the wavelength. So then this becomes PC equals to hc over lambda, and in which the c cancels out, and we are therefore left with P is equal to h over lambda. And what this is trying to show is the fact that a photon with a certain amount of, with a certain wavelength will behave as a particle with a certain amount of momentum, which is also another relationship to demonstrate the wave-particle duality. This is very interesting. It's just showing the relationship between special relativity and as well as how it can be used to apply to quantum, to the quantum field. And anyways, this diagram here on the side, you can ignore it if you want to. I just thought it'd be really cool to show you. But we're just looking at different realms of physics. Right now, we're dealing with the quantum mechanics, which is the particles are moving much less than the speed of light, but we're looking at microscopic scales. So this, while we've been dealing mostly with classical mechanics, which we're dealing with massive particles and they're not moving very fast. But then Einstein is tying his special relativity, which is, we're talking about relativistic mechanics. So this is the work that we usually use special relativity when you think about astrophysics. So this is going really fast, closer to the speed of light for large objects. But then there's another interesting field, which is the quantum field theory, which we talk a new way to model particles on how they move when they're traveling at the speed of light and at the microscopic scale. So very interesting stuff, but just seeding it there so that if you see these kind of things later on, keep in mind of that one. So quantum actually does branch out into quantum. There's quantum gravity, and there is. Anyways, I guess I should stop. Right. Anyways, so we have this relationship here for a photon, which we're saying that the wave here behaves like matter. Now here comes de Broglie, and you might be tempted to call him de Broglie. No, it's French, so. You have to add the in there, the hypothesis. So de Broglie comes in. I found this really funny. He comes in and he essentially takes this equation and says, "Hey, well, if waves can behave as matter, then why can't matter behave like waves?" So kind of going at it the opposite way. So essentially, he wanted to show the fact that, well, if matter is able to behave like waves, then from the momentum of, say, a certain object will display wave-like properties in which the wavelength is equal to h over momentum, essentially taking that relationship and just moving it around. But the idea here is that, well, now that we are saying, hey, well, can't we model matter like waves as well? So that's kind of where the de Broglie hypothesis comes in. One thing I kind of want to mention is that this equation is not in your data booklet, okay? So you kind of have to just know this relationship. Okay, so this is kind of, this is where de Broglie hypothesis comes from. And essentially, we just have to be careful with the application of these equations, especially when we talk about when particles, say, move closer to the speed of light, and what we can use and what we cannot use. So let me do a big summary of, let's say you just skipped this whole video, and you're kind of watching this now. What is it that you need to take away from this? Number one, what you need to take away is this de Broglie hypothesis here is not in your data booklet. So you need to know this equation. You need to be able to apply it. It's essentially describing matter as a wave, potentially. So that's tying together the particle wave, the wave particle duality principle theory. So the next thing you want to know is, based off of Einstein's work on special relativity and the Planck-Einstein relationship here, is that for the energy of a the total energy of a particle uses this relationship here, which it depends on the rest mass, and it also depends on the momentum of this particle. And if we're talking about relativistic speeds, this is kind of where this applies, okay? So you kind of have to know how to use this equation. Certain areas where this applies might be annihilation, pair production, where you have photons of certain amounts of energy, and then that gets converted into into a pair of particles. The other relationship is, and based off of that, we have to be careful, is that when we're talking about smaller speeds, the kinetic energy is just 1/2 mv squared classical theory. But when we talk about relativistic speeds, when the speed approaches the speed of light, you have the kinetic energy of the particle related to the momentum and as well as the speed of light there, okay? So I would say those are your key takeaways from this video. So hopefully this video gives you some background on this, where this equation comes from, which was bothering me at the time, and hopefully it sheds a little bit of light when you can use it, okay? So, of course, we need to apply it and all of these different theories. Let's move on to examples in the next video. Thank you for watching. Fat Mama Physics, signing out.